Hello, this is a screencast about how to simulate data. I'm thinking about when you might want to create some data sets that students can use for their coursework assignments, or maybe in the current climate when they can't actually collect face-to-face data, where you can provide them data sets that address their design and they can carry out the analyses. So there's an overview here, but we're going to talk about the structure of the screencast in this series, the systems, the software we're going to use, random number generators, an important suggestion to use multiple data, create multiple data sets in SPSS. Start with a null effect data set, and we're going to start with a really simple design, the independent groups t-test. We're going to add an effect to one group, a variable for that independent groups t-test, so affect one of the groups. And then we're going to move on to between subjects ANOVA designs up to 2 by 2, and then tidy up at the end the data sets before passing them over to students or using them. So this screencast covers the following. The first 7 of those points, and we're going to make a subsequent screencast covering 2 by 2 categorical data, simulating correlations and within subjects effects, which is more complicated, and simulating regression type designs, simple ones, maybe with 2 predictor variables. So these screencasts are coming soon. So in this one, start by thinking about software systems. Basically, you can use almost any software system that handles and generates data you like. You could use Excel, SPSS, R, Matlab, Octave, Python, many others. I'm going to focus on SPSS here because if you're a sort of coder who's familiar with R or Matlab or Python, you'll probably find it pretty easy to do this once you're fluent in these systems. And even you can do it if you're fluent in Excel pretty easily. SPSS allows you to do this, but it's not something most people learn, and it's a little bit cumbersome, so that's why I'm going to focus on it. Plus, you can generate the data in an SPSS file form, which students are used to handling, and they can access and run SPSS analyses on it. If your students have learned SPSS, you can use any of these other systems as well. And what you would do is save the data in a standard format like Excel or comma separated variable CSV file, and then convert it to a .sav SPSS file at the final stage. Basically, the methods and principles are the same whichever coding system you'll use. Obviously, the specific syntax or the code will vary, of course, from system to system. So an important concept we need to use or understand is random number generators, RNGs. So your system and all of the ones that we've talked about have a way of controlling the random number and using random number generators. So a random number generator just does what it says on the tin. It generates random numbers, and they're drawn from a specific distribution. And different software systems will have different range of possible distributions you can generate from. Typically, most commonly used are the normal distribution and a uniform distribution, but there may be many others. And an important concept is the random number generator seed, which you set at the start so that you can always reproduce the same sequence of random numbers each time. If you continue doing it in an unseeded way, every time you run it, your program, you will generate a different set of data. And that's fine, but it's easier to control and make your data sets more reproducible if you set the seed. And we'll look at this a little bit later. And don't forget the systems vary in their specifics, as I've said before, but the principles are the same across every system. So here's how random number generators work in SPSS. So here's an empty SPSS data window. I'm using SPSS 23, but it hasn't changed much in the most recent versions. So there is, in this menu, transform, I think. Yep, there are random number generators. So you can click on that and you get some options. You can set the active generator, and random number generators based on Mersenne prime numbers. The Mersenne twister algorithm are generally regarded as pretty good, so I'm going to use that one. And we're going to set a seed. It calls that a starting point in SPSS. I'm going to choose a fixed value. I'll use the default, it doesn't matter. It'll always mean that every time I set that, the series of random numbers from that point will be the same. So I'm going to do that. And actually, you see in the syntax window, this little command, set random number generator with send twister, and there's the index. We can copy and paste that into our syntax programs to control a block of random number generation. Okay, so going back to the data window, if I try to compute a variable, transform, compute, you have to have data open or a data file open that's got numbers in it in order for it to work. So you could just type some subject number codes 1 to 200. It's a bit tedious. You can jump down and type 39 here, and that allows you another. You can scroll down another 39, 78, and so on. Enter that, scroll down, and you get and so on in blocks of about 40 lines. It's a bit tedious doing that, and you can type the numbers in afterwards. Now, if I transform, compute, and I can use the random variable, so I can compute a dv equals, and the random numbers here are all in a set of the function groups, and there are lots of different ones. I'm just going to use the rv.normal, and you'll see that that takes the mean and the standard deviation. So we put it up in the expression, and we're going to use a standard normal distribution. A standard normal distribution has a mean of 0, and it has a standard deviation of 1. That's what z-scores are based on. So 95% of the distribution lies roughly between -2 and +2 standard deviations. So we're just going to put that in, and now it will actually compute some values for that. So we look in the data set, we've got, as far as we've created the rows, it will create random numbers. Let's transform compute. I'm going to make it dv uniform, and I'm going to change this, and I'm going to use the rv uniform and put that up there, and it just has the range over which you want the numbers to be uniformly distributed. So a common choice is between 0 and 1. So here we go, we do the same, we create a new dv, and if we look at the data set, we now have another dv. And really, that's all there is to it. So here's some data I made earlier. First, from a normal distribution random number generator in SPSS, using a standard normal distribution, as I've said, often represented with a n brackets 0 and 1, the parameters of this normal distribution. Here's just one example for a sample of 200, and the mean is close to the expected value of 0.06, and the standard deviation is close to the expected value of 1. And it's not perfectly normal, but it's roughly normally shaped, and there's a few quite high scoring positive values. For this particular one, I made a number. This one's called dv7. It's always good to sense check your data at this stage by looking at the variables, and we'll consider this in more detail in a minute. So here are some data that I made using those operations, using the random number generator from a uniform distribution. Remember, I chose it to have a uniform distribution, designated U, between the values of 0 and 1, continuous uniform distribution random number generator. And what we see is we generated 200 simulated participants, and there are 20 bins in the histogram. So if it was perfectly uniform, every bin would have 10 observations in it. And we can see that some do have exactly 10, but there's plenty of random sampling variation around that. But when we look at the overall statistics, we see that the mean is close to the expected value. If the distribution is uniform between 0 and 1, we would expect the mean to be at the midpoint, 0.5, and it is close. And there's even a formula for a random uniform distribution with particular values, which determines its standard deviation. So we could even compare this to the expected value. If we looked it up, we're not going to do that here. So we talked earlier, or mentioned, we were talking about creating multiple data sets. So it's useful to do so, multiple variables and data sets. Why specifically? Well, first of all, if we generate a number of variables, we can check those that have close to the expected value, because we want to be controlling the data. And so by generating them with using particular random number generators, sometimes the mean will be close, as the examples we've seen, to the expected value, and we can use those. Sometimes by random fluctuation, the mean will be somewhere away, and that will perturb the relationships we're trying to build into our data. Secondly, if we create multiple variables and pick several good ones from each, we can create multiple data sets to give to different students. So they'll be different for each student, but they will be formally, structurally identical. Just the precise numbers will vary, which could have some advantages. So we're going to start making this concrete with the easiest design, the two independent groups, which we're going to analyze by a t-test. So we're going to generate data using a standard normal distribution random number generator. And we do this because the t-test, one of its underlying assumptions, is that it requires normally distributed standard deviations of the mean and standard deviations of the difference between the means in the two groups. And to achieve that, if our underlying data has a normal distribution, then the sampling distributions of the means by the central limit theorem will have a normal distribution. So it's, in other words, generated data that's ideally suited or matches the assumptions of the t-test. So we're going to generate our data. This is an important tip, with no effect in there first, the null effect data set. It's much easier to start that way and then add in the effect size that you want in the data set. We'll consider that in a minute. I'm going to generate data with no differences between the groups in the case of our independent t-test. So how do we do this in SPSS? Well, we're going to use a syntax file, and I've prepared a syntax file, and this gives a link in the description below this screencast. So go on the link and it will be able to download the file using that link. Here is the syntax file. It's actually in two parts, and it's actually slightly easier to use the second part for what we're doing today. So here it is. You're just going to essentially highlight this piece of the syntax and run it. But we're going to just go through it very quickly, just so you understand what it is. You'll see I've pasted in the setting the random number seed to be a fixed point. I have no idea why in syntax that is grayed out. Normally comments start with a star are grayed out, but this is grayed out, but it runs. So we always get the same sequence. Create a little program, and we're going to have a loop within the program, which we're then going to have repeats within that, so we can generate multiple lines of data. So we're using a feature of the SPSS syntax. We're going to use 200 participants. You can change that as you like, and it uses this hash I, which is in sort of an indicator of which row in the dataset, which participant you're working with. And then we're going to repeat and creating simulated variables, and we're going to give them names dv1. Well, here for this program it's up to dv 1000. We don't want that many. Let's just do 10. And then within that repeat loop, we're going to do some computations, compute some variables. So we're going to compute group equals 1 for all the subjects, and then if our subject placeholder or indicator hashtag I is greater than 100, we're going to make it group equals 2. So we're going to have two equal size groups of 100 participants each. And again, t-tests work best when the group sizes are equal. We're not deviating from the standard, we're using normal random variables. And we're going to create a subject ID variable in the file because it's just useful, and at equal, we're just going to record that in the file as a variable subject ID. And this simvar won't exist in our file, it's just a label. What we're going to create is dv1, dv2 up to dv10, and we tell it what simvar should be. We're going to compute it and first do dv1 and so on, and in each case it will be rv.normal which was the syntax we saw earlier when we generated, or could have seen if we'd looked, when we generated random numbers previously, rv.normal, and these are the parameters: 0 for the mean, 1 for the standard deviation. We end the repeat, we end the case, we end the loop, we end the file, and we end the program. So this structure seems over elaborate, but essentially it's just like a loop as in any other program. So we can run this program, remembering to highlight the random number generator as well. And then in SPSS, if you run the selection, or you can click on this button here, it will just run the highlighted lines. Here we now run it. And in our syntax, in our output window, it reproduces this syntax, and there's no error message, so that's good. Let's suppress that for the moment. And then we're going to go to the data window, and we'll see when I drag it in view, we've created a set of data with 10 DVs, group either 1 or 2, and the subject ID, if we scroll down, you'll see when I get past subject ID 100, the group number will change. Here we go, subject ID is 100, group 1, and after that it's 2 to the end of the data set. We can tidy up these decimal points, which are unnecessary decimal places, later. And here we have our 10 DVs. Basically, we've simulated no difference between the groups. They all simulate from the same random number generation, so there'll be no difference here. So we can test this out by running a t-test on, in this case, our 10 variables. Let's just do that first. We're going to analyze, compare means, independent samples t-test. And this window, we're going to drag in all our variables. We want to analyze all of them. That's why it's good to not have too many. And we choose the number appropriate to the analysis we're doing. And we're going to put grouping variable is group. We're going to define the groups. Group 1 is 1, group 2 is 2. Continue. And then OK. Now we see we've got our summary statistics for the two groups. We can look at those, but if we look at the actual t-test, it gives you the mean difference. So if each subgroup should have a mean of 0, the mean difference will be 0. So we want values, if we want to pick a representative data set that's close to its expected values, you want these to be small. Fortunately, nearly all of these are pretty small, so we could probably use any of them, but we might pick the smallest ones. There's no difference between, very little difference. We check the significance. Okay, we might get some significant by chance. There's no difference here in any of these. These are all quite close to 0. So we could use any of these. If we chose one which had a big difference by chance, then when we add an effect, that's the effect of that additional effect is going to be compromised or masked or exaggerated by the random effect that we've created here. But these are a nice set. So it's important to generate multiple sets, variables, like I said, to pick ones that we want to use. So now we need to add an effect to one group, because we've generated some t-test data where there's no difference between the groups. But now we want to create some data potentially with some effect in it. So we're at this point. How do we add in effect? Remember, the two groups data were generated using means of 0 and a standard deviation of 1. So what we can do is add an effect to the scores in one group, obviously, and we can add an effect of E, standard deviation units, to one group. And that is because our data are in standard units, 1 standard deviation. And this E could be a positive or negative quantity, depending whether we want one group to be higher or lower than another. And the effect size we generate is measured by Cohen's D as a measure of effect size, and it's simply E. It's this number of standard deviations divided by 1. And that allows us to control the power of the data set by varying the size of E and the amount of sample size. So if that's our Cohen's D effect size, we can use a power calculation software to work out how much power this particular data set we're creating would have based on the sample size. We've chosen 200 with two groups of 100. So how do we do this in SPSS? So here we have our data set, which has, in this case, 10 DVs, subject ID and group, as before. And we're just going to take one of them. We'll just work with DV1, and we're going to use the compute command simply to add an effect size to one group. I'm going to add it to group 2, and I'm going to add a positive effect. And I'm going to add a small but typical psychological effect size of 0.3. So it's really very straightforward. We write transform, compute, we DV1, we rewrite DV1, and we make it equal to DV1 plus our effect size 0.3. And then we make sure if we add this condition in, if, only if, group equals 2. Continue, OK. We're going to change our existing variable. It's important to sense check that result just to check it. So we're now going to analyze just DV1. So we're going to do a t-test, the one we've done before, compare means, independent samples t-test. We look at DV1, and our grouping variable is group as before. Define groups. Drag this in again. 1 and 2. Continue. OK. And what we see is we have a significant difference. We look at the statistics. Our group 1 was close to 0 as built in, and group 2 must have been a little bit above 0, about 0.1 above, because we have a value now of nearly 0.4. So that exaggerated, that small amount of random variation exaggerated the difference and contributed to making this effect significant. And now we have a data set we can use for giving to a student after tidying up to do a t-test. So how can we extend what we've just done to a one-way ANOVA? Well, we want to work to a one-way design with more than 2 groups, because with 2 it's essentially the same as the t-test. So the first thing is that you have to modify the syntax file we used earlier to create more than 2 groups. It's actually very simple to do, and I'll show you how now. So here's our syntax file again, as before. And remember, we had 200 subjects in 2 groups. So first of all, I might make 300 subjects. And if hashtag I greater than 100, and I'm going to just be completely careful here, and hashtag I, oops, capital I, less than 201, put that in group 2. And then I'm going to just make another if statement, Control C, paste it in, greater than 200, group equals 3. And that's all there is to it. We're going to define group 1 as the reference, or maybe our control group or comparison group. And then it's just an extension of what we've done before. We can add an effect of E2 standard deviation units to group 2. That might be positive or negative relative to the 0 baseline that we've built in so far. And then we can add an effect E3 standard deviation units to group 3, and that could be different from E2, and it could be even in the opposite direction, so that we can make 2 groups or more groups, and some of them differ from the reference group. And it's very straightforward to do this in SPSS using the compute command in a similar way to the way we've done it above for 2 groups. So I won't bother showing you that. So how would we extend it to a 2x2 between subjects ANOVA? You're going to need 4 groups, obviously, and you'll need to add in the desired main effects and the desired interaction. that needs a little bit of thinking and is a little bit fiddly. So to how to do this in detail will be covered in a short separate screencast, which you should watch after this one. I've said it's important to get it all sorted with those data generated using standard normal variables. And now we're going to tidy up the data to make it realistic and relate to a cover story or the study that the student is wanting to simulate or that you want to present. So it's much easier to scale our variables appropriately right at the end. So in a recent study which I was attempting to simulate, for example, the DV had scores bizarrely that range from 0 to 114. It's a standard test and that's the range of scores. And in one of the manuals, the source reported that the sample mean for a healthy sample was 81 with a standard deviation of 14. So I'm going to want to turn those variables of the kind I've just generated to match this. So remember, our simulated data has a standard deviation close to 1 and the means in the two groups approximately 0 and E, and I simulating this data I added had an E of 0.5, a medium-sized effect. So the next part of tidying up is to just transform this using what's a simple linear transformation. From X old, your original scores, you're going to turn them into X transformed or X new as I've written here, using a really simple formula that you take X old and you multiply it by a scalar for the standard deviation to turn standard deviation of 1 into what you want it to be, in this case, and you add a mean shift value that shifts the mean from a mean of 0 or E to the higher value. So in my example, I want to match the reported data, a mean of 81, and the standard deviation is 14. So these are the values I'm going to use here. And actually, it's again very simple in SPSS to do this, or any other language. In SPSS, we're going to use the compute command to do this. So here is our data for the simulation. I'm just looking at DV1 and I've arranged it so that group 1 are generated with a mean of 0 and I've added an effect size of 0.5 to group 2. We can just check this. I'll drag in the data output window using a t-test. Here it is. And we can see we've got a good close approximation to the intended values. In group 1 it's close to 0 and in group 2 it's near as damn it 0.5. So that is looking good. So now I want to transform those data to the desired values. I bring in the compute menu again. Here we are. And I write DV1 new. And I always like to keep a new record because if something goes wrong, I have to start again in creating DV1. So DV1 new is the standard deviation that I want, 14 times DV1. And I'm going to add the mean shift, which was 81. As described earlier, and note there's no if. I add this to all subjects in both groups because it's going to have the same effect on both groups, transforming both. One of course will be shifted by an amount which is half a standard deviation, which will be 7 points relative to the other on average. Okay, so I run that. We now can repeat that t-test and we see the two groups are close to what we want, 81 nearly, and a standard deviation of 15.5, close to 14. And this group has a mean of 88, so it's been shifted by half a standard deviation, 7 points, as we said, and still has the same standard deviation. And this effect is highly significant because it's a much bigger effect size than the one we illustrated earlier of 0.3. Well, it was actually 0.4 because of random fluctuation. So there's one final check to make. So what I did was to run descriptives after having split the file by group 1 and group 2. And what you can see is some minor issues that we need to tidy up. So you can see that the values for individual subjects have fractional parts. So one subject had a score as low as 36.26 in this group and the other in this group 53.75. And the scores on our actual test are supposed to be integer 1, 2, 3 up to 114, and a few subjects have obviously got scores above the maximum possible 114. So we're going to need to deal with both of these features to make our data realistic. So first of all, we get rid of the fractional parts by rounding, and there's a simple command in SPSS. So I'm going to transform compute, and I've created a new variable, dv1new underscore round, which is just the rounded version of dv1new, and we click that to go on, and then we're going to do analyze descriptives. We look at descriptives again. We've got the group by group filter. We're going to change that to be dv new round. Okay, and now we don't have anyone that's got a fractional part, which is great. The next thing we've got to do is make sure we clip anyone who scores above 114 to the maximum of 114. So to do that, we can use another transform compute command, and notice I'm just writing it again, dv1 new underscore round. I've set it to be 114 if, using the if option, dv new underscore round is greater than 114. Click OK. It asks you if you want to change the existing variable. That's fine. OK. And then what I've done is run descriptives, and you see that there are no values in either group above 114, and the overall stats look pretty close to our target value of 81, and then 7 higher, and standard deviation is close to 14. So to summarize the final part of tidying up, I've just illustrated we shouldn't forget to remove implausible or out of range values, and make sure integer values are integer, and so on. And then some stuff that is easy to do that I won't show here: give the variables sensible names that match to the design, and use variable labels where appropriate. And don't forget to remove any unnecessary decimal places for integer or intra-coded values as appropriate if you haven't rounded them already. And that's pretty much it. So thanks for listening, and please like the video if you did, and you can subscribe to my channel, and then if you hit the bell notification icon, you'll get notifications of all future screencasts as they're published.